Upgradability patterns are becoming increasingly common, and of course, with that adoption of upgradability, we're seeing a major increase in the amount of upgradability related vulnerabilities. Today, we're going to examine and have a look at 5 different common types of upgradability vulnerabilities, bugs, and mishaps that you'll often see when you're looking at different code bases that are undergoing a security review or possibly even in a smart contract contest. And after watching this video, you'll have 5 things that you automatically know to check for when you're looking at specific types of proxies, upgradability patterns. You'll be comfortable reviewing any type of upgradable contract. So we'll get into these 5 common vulnerabilities in just a minute, but of course, before we do that, my name is Owen, and over 2 years ago now, I founded Guardian Audits, and ever since then, we've uncovered easily over a couple hundred of critical and high vulnerabilities across auditing thousands and thousands of smart contracts at this point. And I've personally spent easily a couple thousand hours reviewing smart contracts. And my goal with this channel, everything I put out, and especially this video, is to take all of my experience, everything that I've gone through thus far, and distill it down so that you can ultimately become a much better smart contract auditor, security researcher, blockchain developer, whatever it is that you are looking to be in a fraction of the time. So with that out of the way, let's dive into these 5 different types of common upgradability vulnerabilities that you can start looking for today. All right, amazing. So we're about to dive into 5 different types of upgradability vulnerabilities and bugs. But right before we do, I want to make sure that each of these that we're going through, you're actually remembering and are actually going to be something that you notice when you're looking at smart contracts in the future. So for any one of these that you didn't previously know about, or is maybe a new concept for you, make sure to keep track of this stuff, take notes, and have a spot in, either ideally maybe it's a notebook, or ideally maybe it's online in something like Notion or something like this. Keep track of the new vulnerabilities that you didn't know about. And this way you can almost have a checklist of things to go through when you do encounter upgradable contracts. With that out of the way, let's dive into the first of these 5 common vulnerabilities or findings that you can get relating to smart contract upgradability patterns. And of course, to start this off, we're going to be talking about storage gaps. I'm going to first explain the scenario in which storage gaps come up and why they're important, and then we're going to see, exactly what can go wrong if you don't have storage gaps and why this is a finding. So first of all, let's imagine the following scenario. Let's say we have a smart contract here, our trusty rectangle representing a smart contract. And let's say that this smart contract here is actually inherited by another smart contract. So we have a smart contract below it in the inheritance hierarchy, and it is inheriting from this smart contract. Now, let's say that there happens to be a storage variable defined in this first higher level contract. So let's say this is, at slot 0, we have the storage variable A, and then perhaps at slot 1, we might have the storage variable B. And then that means that when we inherit here in this contract, which is the base level contract that is inheriting from this contract, then it is slot 2 might have storage variable C, and then we might see, a slot 3 has a storage variable D. That's all fine and completely working as expected, right? We've just got, some storage slots allocated. The first storage variables go into the first slots, and of course in the hierarchical smart contract, the storage variables that are in that contract come first, so they get the 0th slot and the first slot, and then the 2 storage variables in the base smart contract, which is inheriting from the higher one, get the storage slots after that. So we get the storage slot 2 and 3. So this is all fine, but let's imagine what if we were to upgrade this set of smart contracts? So let's say that this was the implementation contract for a proxy. So let's imagine that we had our proxy here. And of course, really quickly, if you are not familiar with what a proxy is, you're not familiar with what a transparent proxy pattern is, a UUPS proxy is, or anything like this, then go and watch the 5 upgradability patterns video. The link will be in the description to that, and that will completely address everything to do with proxies, all the different upgradability patterns, so that you'll know exactly what we're talking about here. So this is our proxy. Let me just put proxy right here. And so let's imagine that this was the implementation contract. So this is the implementation contract right here. And so I'll put implementation. And of course, it just so happens to inherit from this, base contract. So we'll just call this a base contract. And this is higher up in the hierarchical order. Implementation contract is base contract. That's how this will work. So the proxy, let's say, is going to accept calls from users, is going to delegate call to the implementation contract, and that's all fine and dandy. But what happens if we want to upgrade this implementation, this base contract? So we're going to take and swap out, and instead of using these 2 contracts, we're going to use the newer versions of these 2 contracts. So let me copy and paste. We got our newer versions of these contracts. And now let's say in our new version of these contracts, I've also introduced a 3rd storage variable, let's call it X, here in this base contract. So that was just a part of the upgrade, is we included new logic. That new logic just so happened to go into the base contract here. And we want to support this new variable now. Well, let's see, where does this fit in the storage slots? So still, of course, slot 0 is A, slot 1 is B, but now this X variable goes to slot 2, which means that now this C variable will go to slot 3, and this D variable will go to slot 4. And so we have a problem here, because the original value for this second slot, it is the value for C. So immediately when we are reading from slot 2 to access, okay, what is the value of X right now? Since we're using a proxy, right, all of this storage is actually in the proxy, right? So I'm writing these slots in the implementation contracts, but really all of this storage is actually stored in the proxy. So here's what the proxy storage looked like before the upgrade. We had slot 0 was A, we had slot 1 is B, slot 2 is C, and slot 3 was D. This is what the storage looked like of the proxy before the upgrade. And now what we're trying to do with the upgrade is, now we're saying no, this is now X, and now we're shifting C down, so this is now C, and then the 4th slot will be D. And so this is an issue, because we're going to be now reading, when we read the value of X in this base contract for the implementation logic, when we try to read that, we're going to go to slot 2. We're going to see what is the value of slot 2. Well, initially it's going to be the value of C that was left in there. So we're reading the value of C for X, which is, these are 2 completely different variables. And this almost always will cause some sort of critical logical error in the smart contract system. So this is a very specific type of storage collision where, by way of appending new storage variables to the base contract here that is being inherited from, we are pushing down all of the other storage slots for the variables in the implementation contract that inherits from the base contract. And so we get some, mixing and matching of storage slots that won't even really make sense in terms of the implementation's logic. So how do we fix that? Well, that is exactly where storage gaps come into play. So in our original base contract, since we know that this system is going to be upgradable, what we need to do is we need to add some padding. We need to add some space between the storage slots in the base contract and the storage slots in the implementation contract so that we can safely add things to the base contract if we want to. So we'll go ahead and you'll often see a list of, like, let's say 48, and we'll call this underscore underscore gap. This is how you'll most often see it. And what we're doing here is we are basically reserving out the next 48 slots for this base contract. So there's nothing actually stored in them as of right now, but since we've declared this variable, we've immediately gone and used slot 2, 3, 4, 5, 6, all the way up until slot 50. And so what will happen is this slot will be 51 for the C variable, and this slot will be 52 for the D variable. And now what we can do, since we have this gap, is we're able to upgrade to a new version where we just decrement the gap here by 1 and we just add in our new variable. And so now it's perfectly fine. We'll have A, B, X. We will have all of this gap space. And then at the same slot, we'll have at 51, we'll go C. And then at 52, we'll go D. And so now when we read and we want to read C, we're going to slot 51. And we're still going to slot 51 to get C in this example. So now none of the storage slots have been changed here. We have simply added a single X variable in that second slot. So this is just a way to give each of these base contracts that are inherited from their own padding, their own area for new storage variables to potentially be added in the future when the system is upgraded. And so let's have a look at this storage gap in action. Let's see what it looks like in a real contract. So let's go ahead and have a look at the ownable upgradable contract that is using the storage gap from OpenZeppelin. So we've got an owner storage variable here, right? This is necessary to track who is the owner of the inheriting contract. And we can see if we go down to the bottom of this, we've got a storage gap. I can zoom in, we can see we've got a storage gap right here of 49 slots. And then of course a note here that says this space is put to allow future versions to add new variables without shifting down storage in the inheritance chain. And so that is the first of the 5 common vulnerabilities and mishaps that you'll see with upgradability patterns. But now I want to talk about a new solution to this sort of storage gap problem that is being adopted. So let's have a look at the most up-to-date version of this ownable upgradable contract. So if we scroll here, we can see no longer do we actually have a storage variable for the owner. In fact, we can see there is the ownable storage location, and then inside of the ownable storage is where the owner is stored, the address of the actual owner. So this is called namespaced storage. And this solution completely sidesteps the need for a storage gap. And this is because what we're doing here is we are storing the storage for the base contract here in not just whatever the first couple of slots are, but we're specifying it instead of saying, okay, A is just going to go to slot 0, B is just going to go to slot 1. What we'll do is we'll often just package up A and B into a single struct, which is called like the underscore storage blank storage, where blank is whatever the name of the contract is. And then we will put these, so these will then start, so the storage struct will begin at the storage point that is corresponding to the hash of some string, often including the name of the base contract. So this would be slot like some random huge number that is resulting from a hash, and that would have the first thing that is in that struct, the first full storage slot for that struct, and then of course the very next slot would hold the next thing, the next 256-bit thing in that struct, which would hold B for us, and there is no need for a storage gap because, of course, these are just stored in some completely random storage slots. So then when we come here, there's now C would be the first actual just straight up declared storage variable, and so the Solidity compiler will put C in the 0th slot, and then D is the second, so it will go into the first slot. And this is completely fine, right? We have, if we're going to access who the owner is, we're going to go and use and look up in this completely random slot. So here, for example, is said completely random slot. This is the result of catch-at caching this string, and then ABI encoding it and ANDing it with some extra bits here just to increase the randomness of this location, and then finally hashing all of that again. And that is how we get the location where we are storing. So we are grabbing this slot and returning that slot as the ownable storage. If we want to get the owner, then of course we are getting the ownable storage, and we are returning the owner address from the ownable storage. So that is a brief introduction to what is namespace storage. It's everything you need to know about namespaced storage. So now let's have a look at the second of these common upgradability vulnerabilities. So I've got a UUPS implementation contract pulled up here. Now, can you see what the issue is here? There's actually a couple issues, but can you see what the first, maybe most obvious issue is? Maybe pause it and have a look, see if you can figure it out. Well, maybe you found it, maybe you haven't. The first issue is that this UUPS implementation contract is using not the upgradable version of ownable. So this goes back to the first issue we were really discussing, is that if we just had a normal contract with variables that are just declared in the base contract and we wanted to add a new one, then if there's no gap, if we're not using namespace storage or anything like that, then we're going to end up with some storage collisions here, because X is going to be attempting to write to C, and then C is going to overwrite D, and all of this messy stuff. We can see the regular ownable contract here that has a regular storage variable declared. And if we scroll to the bottom, there is no storage gap. They're also obviously not using namespaced storage. So this is exactly the issue that we will run into when we're attempting to do an upgrade with this system. So what we need to be doing is we need to be using the ownable upgradable. So ownable upgradable from, oh, and there we go. We automatically have it in. So we're going to use ownable upgradable, and then we do not need to actually call the ownable upon construction, but upon initialization, then we need to ownable init, and we need to provide the initial owner here. And so if we look at the ownable upgradable, we can see that this most recent version of the ownable upgradable, like we saw, is using namespaced storage. And so now, of course, we have this solution where the base variables here, like the ownable variable, will go into some completely random storage slot, and we will not be having to deal with any weird slot remappings or anything like that upon upgrade. So that is the second common vulnerability. So this one is somewhat similar to the first one. So in the first one, you want to make sure that if you see contracts that are made by a protocol team specifically, and they're meant to be inherited from by contracts that are upgradable, you want to make sure that those contracts, the ones that are higher up in the hierarchical structure, are first of all either using storage gaps between storage variables or using namespaced storage. And then as a part of this second one here, you want to make sure that if a implementation contract for an upgradable contract is inheriting from, some popular libraries like OpenZeppelin, like we saw here with the ownable contract, you want to make sure they're the upgradable versions of those contracts. And now, as our third common vulnerability with smart contract upgradability patterns is to not be using this ownable init here, or the specific init initializer for a contract that you are inheriting from. So let's talk about exactly why we need to use these init functions. Well, when you have an implementation contract, so let's say we've got our proxy right here, here's our proxy, and then here's our implementation contract. Now, the implementation contract is deployed independently of the proxy getting set up and starting to use this. So when you deploy the implementation contract, you run the constructor, but we don't really care about what was run in the constructor because this is just an implementation contract. This is not the actual system itself, right? When we deploy the proxy is the contract that holds the actual storage in the storage slots, and this is the actual state of the system. So when we deploy the proxy, then we want to be able to do something to be able to run some like constructor-like code in the proxy. So the proxy can call initialize, so some sort of initializer functions. So like we can see here, we have an initialize function, and what it will do is it will act as if this is kind of like the constructor for an implementation that is being used. So we can't use the constructor. Instead, we're going to use initialize. And that is why we have ownable init here, and it's very important to be able to assign the initial owner, right? And this is similar to what you would see in a regular ownable, where you have in the constructor, we are just transferring ownership to the initial owner. If we go to the ownable upgradable, we are transferring ownership to the initial owner. And so that is the third common mistake here, is oftentimes you'll see that a contract might inherit from multiple of these different upgradable contracts, but it might forget to use an initializer or use all of the initializers for a specific upgradable contract. And that can leave the system in a really invalid state and obviously will lead to some critical bugs and vulnerabilities along with that. And then, of course, to go with that, we have the fourth common type of vulnerability that you'll see, which is a really, really unfortunate one, which is that the initializer modifier is not used where it should be. So let's imagine this function did not have the initializer modifier. Then anybody could obviously call this at any time, and they could become the owner by the way of using this ownable init function. So in the case of the ownable upgradable contract, there is some safety guards here where we have the only initializing modifier being used for this, but in some cases, a malicious actor might be able to cause some really, really catastrophic damage by calling what is meant to be an initialize function when the system is not initializing. So let's have a look at this initializer modifier and let's see what this does. So in the initializable contract here, which remember we are inheriting from initializable. And so first of all, you'll notice that we're using namespaced storage. So obviously this initializable contract is compatible with upgradable contracts. And then we're checking a few different storage variables in that storage struct. So we have the initializing and we have the initialized. So we're checking, is this a top level call? Meaning, is this the first call that has an initializer modifier on it? And then has the system already been initialized? When you're first calling an initializer, initializing will be false. So not initializing will be true, and is top level call will be true. Initialized will be false, or it will be 0. And so initialized will be 0. And so if we see, okay, is this the initial setup? Initialized equals 0 will be true, and it is a top level call, so true. So this is indeed initial setup. And then construction is if it has been initialized and the code length is 0. So this will not be true for us because we haven't been initialized yet. This modifier will only allow execution to occur if it is either the initial setup or if we are in construction. So this would be meaning if a proxy is literally being deployed right now, because remember, when we're calling this from a proxy, we're delegate calling, and so address this will refer to the proxy, and then we will set initialize to true. So you call this once if it was not initialized, now it is initialized, and then while we are within the execution of this, while we're executing whatever function has this modifier, initializing will be set to true, and then afterwards it will be set to false. And so that's where you see in the ownable upgradable, this only initializing modifier will go ahead and check initializing, and they will basically just read is initializing from the initializable storage. So this ownable init will only be able to be called during an initializer. And of course, that protects us. If we were to make such a mistake, then it's not as if any attacker would be able to assign themselves as the owner, but what would happen is nobody would be able to initialize this, not even the proxy, because that initializing state wouldn't get set. And so this ownable init would just revert, and then basically the proxy would just be useless. However, in some other initialize functions, there might not be such a protection. And so we want to always make sure that we have the initializer modifier for initialize functions. And you'd be surprised how many times this could actually come up in a real code base, in a real security review, that an initializer is missing. And then finally, before we move on to the fifth common vulnerability here, I want to talk about this disable initializers that we see. So when we're deploying the actual implementation contract, like we discussed here, we're not actually interested in using the constructor, or really we're not interested in the state of the implementation contract at all. And so what we do when we disable initializers is we are setting the storage for this implementation contract. For this implementation contract, we're setting the initializable storage to initialized equals type uint64.max. So we're setting initialize equals type uint64.max. This is not setting the state for the proxy contract. We're setting specifically the state for the implementation contract. And so when initialized is not equal to 0, we assigned it to something that was specifically not 0. Now you will never be able to call the initialize function on specifically the implementation contract because of the storage that is in the implementation contract. The only way you will be able to call this initialize function is if you are calling it through delegate call through, for example, our proxy, which does not have initialized equals the type uint64.max. Instead, initialized here is, of course, initially 0. And so when we attempt to delegate call that initialize function through our proxy, it will actually work. But if you try to call the initialize function on the implementation deployed contract itself, then it will fail, because of course we don't actually want anybody to interact with the implementation contract, because that doesn't make sense. The state of the application is not dependent on the storage of the implementation contract. And finally, so what is the fifth common vulnerability that I've actually seen in a real security review? Well, it just so happens to be that when you're using a UUPS upgradable contract, of course you must override. So if we go to the UUPS upgradable contract and we go ahead and see in this upgrade to in call function, first what we do is we authorize the upgrade. Remember, there is no access control on this upgrade to in call function. And so if you just expose this function without overriding the authorize upgrade function, which has no implementation, then anybody can call this upgrade to and call function and upgrade to any arbitrary implementation for the UUPS proxy. So of course, as they recommend, you're supposed to override it and specifically add access control. So a lot of times what I'll see is this authorize upgrade function overridden, but without the access control. And so I've actually seen this in a real security review. And in the particular version of UUPS upgradable that they were using, there's an upgrade to function and there was an upgrade to and call function. And so they only overrode the upgrade to function with access control. They didn't override the authorize upgrade. And so attacker was still able to call the upgrade to and call version of the upgrade function and assign any malicious implementation. So always just go ahead and override the authorize upgrade function and just use the only owner or whatever access control for that, and don't even bother overriding specific upgrade functions. This is exactly how OpenZeppelin recommends upgrades to be authorized. So there you have it. There are 5 common vulnerabilities and bugs and mishaps with upgradable contracts and different upgradable patterns. I hope that at least a couple of these were maybe something that were new to you, and hopefully you'll be able to go on into some contests or some security reviews and uncover findings similar to this based on these heuristics and ideas, and hopefully this can be overall useful to you. And so with that out of the way, of course, if you're really interested in this Web3 security stuff and you're looking to become a fully fledged senior smart contract auditor, an elite security researcher in a matter of months instead of maybe a couple of years, then I gave a rundown of exactly everything that I would do to get there as efficiently as possible. You can go ahead and get that guide in the description below, my 6-step guide to become a senior auditor in 6 months. So if that's something you want to do, then that is there for you. If it's not, then that's perfectly fine. And of course, if you're interested in connecting with people from across the world and you really do love this security stuff, then I'd like to invite you to join our community of security researchers. We've got about 1,000 security researchers and people who are just interested in Web3 security from across the world in our community. You can apply to join the completely free community at lab.guardianaudits.com. All right, and with that out of the way, I look forward to seeing you next time.